Time for more practice, right? The more we practice, the better we get. This set of problems is really just sort of a fun cool down after some of the other practice problems that we've done. But it's good because we get to see some more variation of problems, things to think about along the way. Now, as you're doing these problems, make sure you have your table of Laplace transforms handy, because at some point we'll probably see some Laplace transforms, and that's going to show up on the exam. And of course, we get the table, so it's good to know how to use it. All right, let's get going. First problem. Find a solution to x double prime plus 5x prime plus 7x equals 13 e to the minus t sine t. All right, well, to begin, what do we see? Well, we see this part over here, this 13 e to the minus t sine t, that says it's a non-homogeneous problem. And the nice thing about the form of that, the e to the minus t sine t, well, that tells us that we're really looking at something that undetermined coefficients works well on. Because it's the form of something that which we can say, aha, we know roughly what the answer looks like up to constants. Now, the first thing we should check is what's happening with our homogeneous problem. Okay, so let's check in with that. So we look at x double prime plus 5x prime plus 7x equals 0. We convert that to a polynomial, r squared plus 5r plus 7. And, well, doesn't seem to factor in a nice way. So let's throw it into the quadratic formula. And so we say, okay, r equals negative b plus or minus the square root of b squared minus 4ac. So 4 times 1 times 7 is minus 28. All of that over 2. Now that's negative 5 halves, right? And then here, square root, well, inside will be negative 3. So plus or minus square root of 3i over 2. And now we're like, oh, are we going to have to deal with answers that involve square root of 3 over 2? Ugh. But actually we don't. Because look what the question asks. You know, it's always important to know what is the question asking us to do, which also is what is the question not asking us to do. And if you see, there's this beautiful thing here. Find a solution, one solution. So it doesn't mean we have to find the general form of the solution. It doesn't mean we have to find some solution that satisfies certain initial conditions. We just have to find a solution that works. And what we can do is say, okay, we can be satisfied if we find just one particular solution. So really, we say, aha, we're after finding a particular solution. And now, the key thing here is that these roots don't overlap with our function 13e to the minus t sine t, right? Because what would these roots be to have an overlap? Well, the roots here, the part upstairs in the exponential function, that's the real part. And then here, sine t, that would be I. So these don't overlap. And really that's all we need to know, is to say, okay, now that I know they don't overlap, well, forget it. I don't even need to know what the particular solution, the homogeneous solution looks like. That's not my concern anymore. Okay, so that's good. That's as far as we need to go with the homogeneous part. So what happens now? Well, now we say, okay, good. That means that there's no bumping required. And so let's find out, what does our particular solution look like? In other words, what's the form? Now, how do you go about it? Well, the answer is, you look at the function, you say, okay, my answer will involve that function. So some constant of that function. So a e to the minus t sine t. And we know we don't need to bump, because that's what the homogeneous part tells us. And then we remember there's two rules. If there's powers of t, gotta work your way down. All right, no powers of t, so we're fine there. If there's a sine or a cosine, come in pairs. Ah, there is a sine. So we have to put the cosine pair. And you might say, Do we really have to? And the answer is yes, because actually when we have a complex root, that's where we get the sign from, is from complex roots. But this really isn't one root being represented in the sine function. It's actually two roots that were combined together. And so we actually say, well, since there are two roots, there's sort of a second corresponding pair which came from those two roots. And so we should always have them come in pairs. All right. So now we have our form for our particular solution. Well, we're going to plug it in eventually, but it looks like we're going to need to take some derivatives first because we need to know what's x prime and what's x double prime. Okay, well, so now we're just going to work through the process. xp prime. All right, here, well, no big surprises. Product rule. So derivative of the first minus a e to the minus t sine of t. And then the derivative of the second. Well, the derivative of the second is cosine. So plus a e to the minus t cosine of t. We'll do the same thing here. We'll have derivative of the first minus b e to the minus t cosine. And derivative of the second. And, it'll also be a minus b e to the minus t sine. Now we'll combine. Derivative of cosine is minus sign. That's why there's the minus sign there. And so when we combine, we'll group. See how we have e to the minus t sine t showing up twice? So minus a minus b e to the minus t sine of t. And then here we have plus a minus b e to the minus t cosine t. All right, there's derivative number 1. Derivative number 2, very similar process. And we just work our way through it. So derivative of the first, minus comes down. So we can actually write this as a plus b e to the minus t sine t. So that's derivative of the first term. And then plus minus a minus b and e to the minus t cosine of t. And okay, that's derivative of the second. Now come to this term, derivative of the first, minus comes down. So, well, all right, we can write that as b minus a, right, because minus comes in, flips the signs, e to the minus t cosine of t. And derivative of cosine is negative sign. So again, b minus a e to the minus t sine of t. So we flip signs because derivative of cosine is minus sign. All right, well, again, we group. So e to the minus t sine t, what do we see? Well, we see a plus b, and we see a b minus a. The a's cancel, and it's, well, I guess it was meant to be. Oh, come on. You know we got to do that. 2b e to the minus t sine of t. All right, how about here? Here, the minus b plus b cancel, so it's minus 2a, and that's e to the minus t cosine of t. All right, great. So that's what we have for our second derivative. Now that we have our derivatives, we can plug it into our equation. And, okay, so that's our next step. So what we'll do is we'll have our 2b e to the minus t sine of t minus 2a e to the minus t cosine of t. Second derivative plus 5 times minus a minus b e to the minus t sine of t plus a minus b e to the minus t cosine of t. All right, that's plus 5x prime. And we're running out of space, so we'll go to the next line. Plus 7, just the function, a e to the minus t sine of t plus b e to the minus t cosine of t. And all of that equals 13 e to the minus t sine of t. All right, good. We're rounding the corner. We're almost there. Now, what do? Well, we group things together. So, we have the e to the minus t sine of t. Okay, so what's there? There's the 2b, and we'll just write these down. Then there's the 5 times minus a minus b, so we can write this minus 5 times a plus b. And then there's the 7a. All right, and then we're going to add to that, we have the e to the minus t cosine of t, and we have minus 2a, and we have plus 5, a minus b, and plus 7 times b. All right, and all of that equals 13 e to the minus t sine of t. And the punchline is, of course, that this coefficient has to be 13 to match on both sides, and this coefficient has to be 0 because, well, there's no e to the minus t cosine t on the other side. Okay, so we get down to our favorite thing, 2 equations, 2 unknowns. And, well, maybe it's not our favorite thing, but it's definitely something we got lots of practice with over this semester. All right, well, let's clean this up. So let's see, what do we have here? 7a minus 5a makes 2a. And then we have 2b minus 5b. That's minus 3b. And that altogether needs to equal 13. And then over here, well, we have minus 2a plus 5a. That makes 3a. And on the other hand, we have minus 5b plus 7b makes 2b. And that needs to equal 0. All right, 2 equations, 2 unknowns. Well, now we just have to solve. And there's lots of ways to do it. And, well, okay, let's try the following. Suppose we multiply the first equation by 2, and the second equation by 3. Now you might be saying, what are you doing? Well, I'm going to cancel the b's. So if I multiply it by 2 here, I'll get 6b with a minus. Here I'll get 6b with a plus. So if we do that computation, okay, so the b's would cancel when we combine. We'll get 4a plus 9a gets us 13a. Well, that's kind of a nice number in this problem. It would equal 26 plus 0, so that would equal 26. So that says, oh, a has to equal 2. All right, now that we know a equals 2, well, let's say plug it into this second problem. We get that 6, 3 times 2, plus 2b has to equal 0. All right, well, that's not bad. That says b better be negative 3. And so now we are basically done. The only thing left to do is to say we know what a and b are, so we plug them in. And so we get that our particular solution would be 2 e to the minus t sine of t and minus 3 e to the minus t cosine of t. And that's it. There's our answer. 2 e to the minus t sine t minus 3 e to the minus t cosine t. Ah, what a nice answer. Okay, well, in some sense, the problem isn't so bad. The idea is not so bad, right? We run the process, we check the homogeneous to see if we need to worry about bumping, set up our form, figure out what our derivatives are, plug in, solve for our coefficients, and put it all together, and life is good. Of course, always make sure you know what question you're answering. Are we after one solution, which usually means find the particular solution? Are we after a general form for a solution, which means we also need the homogeneous, but we have arbitrary constants? Are we after a particular solution with initial values? And so, depending upon what you're looking for, you have to tailor it to make sure you answer the question. But we're good to go. What a nice way to start. Fun problem. Woohoo! All right, well, let's hope they're all fun. Of course. They would never give us a boring problem. Well, that would just be rude. All right. So, number 2. Consider the system of differential equations. We have x double prime plus 3x prime minus 2x minus 5y prime plus 2y equals 0, and 4x prime minus 6x plus y double prime plus 7y prime minus 8y equals 0. And there are some initial conditions. X of 0 equals 2, y of 0 equals negative 3, x prime of 0 equals 5, y prime of 0 equals 1. Now, rewrite this as a first-order system in the form x prime equals ax, where A is a 4x4 matrix, and give corresponding initial conditions x of 0. All right. Now, what's going on here? Well, what's going on here is this is one of the things we learned is how we can transform a high-order differential equation into a first-order system. So there was that translation. Now, this just says, hey, we can take a high-order system and do the same thing, right? Where we can translate it into a first order. And so we just got to figure out, okay, what's going on? How does this work? And the way it works is we'll sort of introduce some new variables here. So normally when we think of x prime equals ax, well, and we're told it's a 4x4, right? So what we have is we have 4 things we're trying to solve for. x1, x2, x3, x4. And so those are our 4 functions we're solving for. Now we just have to say, well, how do these match with what we currently have? Well, we can match them in a couple of ways. Now the key idea is you look at what you have and you build your way up, right? So we have x and y. So okay, let's make, we'll say x1 is x, and x2 we'll say is y. And now, notice we have x double prime. Okay, so what we really should do is if x goes up to second derivative, we're going to have every derivative up to that point. So, all right, well, let's make x3 be x prime, and x4 we can make be y prime. All right, now, so those are what we're going to call our variable names. Okay, so let's figure out what we can do. All right, well, let's start by saying what happens. Well, if I look at x1 prime, well, according to this, that's x prime. Okay, now, what do we want to do? Well, we want to write x prime in terms of x1, x2, x3, x4. Hey, I see x prime already. That's x3. All right, and we're done, right? Because we wrote x1 prime as some combination of x1, x2, x3, x4. Okay, well, that was pretty quick. What about x2 prime? Well, according to this, that's y prime, right? Because just derivative of this equals derivative of that. And again, we want to write y prime in some way as a combination of these. And we look at this and say, hey, it's right there. Woohoo! Yeah! X4's in the house. Okay, great. Good. We're halfway done. And it feels like we barely even started. Well, the interesting half is about to start. Okay, what about x3 prime? What would that be? Well, that would be x prime prime, right? Second derivative. And now you're like, I don't see a second derivative there. Where do we see a second derivative of x double prime? Or sorry, second derivative of x. Right there. So let's use that. So what do we have? We have x double prime. If we move this across, that would be minus 3x prime plus 2x plus 5y prime and minus 2y. So we're solving for x double prime. Now, we look at these and say, oh, wait a second. We can replace these with our variables, right? The x prime, that would be x3. So minus 3x3. The x, well, that would be x1. So plus 2x1. The y prime, that would be x4. So plus 5x4. The y would be x2. So minus 2x2. And so we say, perfect. We can write x double prime as combinations of our four functions. Now, let's write it down here, but we'll switch the order up. So we go in the order that we have. So x1, there's 2x1, minus 2x2, and minus 3x3, and plus 5x4. Okay, good. All right, one more to go. And probably you're going to see where we're going here. x4 prime. Well, that's y double prime. Okay, we say, hey, there's a y double prime. Well, let's come up here. We solve for y double prime. We would say that's minus 4x prime plus 6x minus 7y prime plus 8y. And we do the same thing. Well, x prime is x3, so minus 4x3. And then 6x would become 6x1. 7y prime, well, there's x4, so minus 7x4. And 8y would be x2, so plus 8x2. And again, let's change the order up. So we'd have 6x1 and 8x2. And let's see, what do we have? 4x3 and 7x4. And now we're like, great, perfect, because these are our coefficients. So we now can write down our matrix form, right? So what we're really interested in is x prime equals, because we want to write it in that form. And now for x1 prime, we only want an x3. So we have x1, x2, x3, x4. For x2 prime, we just want one x4. So there's x1, x2, x3, x4, right? Because we're reading off, these are the coefficients, x1 coefficients, x2 coefficients, x3 coefficients, x4 coefficients. Now for the next one, it's a little bit easier to see, right? It's 2, minus 3, 5, and 6, 8, minus 4, minus 7, and times x. So there's our system. What's our initial conditions? Well, x0. Well, now we just say, okay, we want x1, 0, x2, 0, x3, 0, x4, 0. So that means what is x of 0? 2. What is y of 0? Negative 3. What's x prime of 0? 5. And what's y prime of 0? 1. And that's our system. So we can translate our system, which has two equations, into four equations, but now there's just a single derivative. And so we could use matrix techniques. Now the nice thing is we don't have to solve it. This is a rewrite it. But now if we had machinery that says, oh, if you give me a matrix, I can tell you the answer, then we're in great shape because it's like, hey, I have a matrix. And the machine will be like, woohoo, I can give you an answer. So this is why this kind of question is actually a nice idea. So, okay. So this one's not such a bad problem if you understand the concepts. If you don't, you're like, what? What's going on? And you spend a lot of time scratching your head. we really hope you understand concepts. Concepts are so much more important. We're not trying to train you to become calculators. We want you to become thinkers, because those are the people who solve the important problems in our world. Okay, anyways, that was our second problem. And all right, we're having a lot of fun. Let's go on and keep going. Okay, next problem. Good, number 3. Write the general form for solutions of x prime, where we have -1, -6, 3, 5x. How nice. It's really clean. We don't have to find a particular solution. We just need to find our general solution. And this really says, hey, let's use eigenvalues, eigenvectors. And let's see what we get. All right, so we start out as we would for any problem where we have to do eigenvalues, eigenvectors. First off is eigenvalues. Okay, so we can look at lambda I minus a, or a minus lambda I, whichever one you want. We're going to take that determinant, and of course we set that equal to 0, and we're going to solve. So what would we have? That's the determinant of lambda minus 1 makes it +1, and 6, and -3, and lambda -5. All right, so take that determinant, and we would get lambda +1 times lambda -5, and then subtract -3 times 6. And, that'll become lambda squared, and then we have a plus a lambda, a -5 lambda makes -4 lambda, and then -5, and plus 18, right? Minus makes plus, and that's plus 13. All right. Well, what are the roots? Does it factor? Doesn't look very promising, does it? And okay, well, what to do? Well, we can throw it into quadratic formula. We've done quadratic formula before already on our practice test. The other thing, of course, is completing the square is another option. We should practice a little bit of that. Right? So this is lambda squared minus 4 lambda. Divide -4 in half, then square that. -2 squared is 4, so that'd be +4 plus 9, which would make this lambda -2 squared plus 9. And remember, that equals 0. So that tells us lambda -2 squared is -9. And this is sort of a signal our numbers are about to get a little bit complex. All right. Well, that tells us that lambda -2 is plus or minus 3i. Or, we see our roots, our lambda is 2 plus minus 3i. So, we're going to get some complex numbers in this problem. Don't worry, don't panic. This is not the time for panicking. Panicking comes later. In our test, we are calm. We are calm, we are collected. We can do these things because these are not the first time we've encountered these problems. Complex roots means that we're going to have things of the form e to a power t, and then sine and cosine of some t. Okay, so what to do now? Well, the next step is let's get our eigenvectors. And here's the thing, is when we have complex roots, we just need one of them. Okay, so for lambda equals 2 plus 3i, and you're probably saying, wait, why do we only just need one? There are two eigenvalues. This is the great thing about complex roots, is they work in pairs. And we'll get to how we get our two answers, even though we only do one eigenvector. It's a wonderful idea. And but you probably already know where it's going, right? But we'll get there. Okay. All right, come on, back to work. Okay. So 2 plus 3i, let's set up, and if you want, we can do it as the augmented matrix where you have the lambda I minus A, and then over here you have 0, and so you get your zeros. 0 here being the 0 vector. So put lambda as 2 plus 3i, so 2 plus 3i plus 1 is 3 plus 3i, and you get 6, and downstairs minus 3. And here you'd have minus 5 would be minus 3 plus 3i. All right, now what do you do? Well, the answer is you're guaranteed, 100% guaranteed, that these two rows are going to cancel in the sense that one row is a multiple of the other. Now, the question is, well, which row do you want to keep? And you can keep whichever one you like. Now, I like that second row because it has all 3's. So I'm going to say, okay, I can cancel off the first row. And now what? Well, now what we have here is we say, okay, if we're thinking of our vector that we're looking for, suppose it has the form A, B, then what has to be true is we need minus 3A plus minus 3 plus 3i b has to equal 0. Now we can move, right, because those are our coefficients, minus 3 times a, minus 3 plus 3i times b. And, well, I can move the 3a across, and I can divide by 3 because everything has a 3 in it. That's why I like that second row. Everything had 3's. So if we do those two things, we come to our conclusion that a looks like negative 1 plus I times b. Okay, that's pretty clean. So that says our eigenvector has the form of, well, negative 1 plus I times b, or b, negative 1 plus I, 1. All right, good. And of course, that's not unique. You can choose b to be anything. You can even choose b to be a complex number and get other eigenvectors as well. All right, well, where do we go from here? We have our eigenvalue. We have our eigenvector. And now what we do is we combine them together. So we do it by splitting them up. So we're going to take our eigenvector and we're going to break it up into the real part, so the parts without I, and the parts with I. So that's our real part, our imaginary part. Okay, so that's our eigenvector. And then we're going to have our eigenvalue. Now that's going to correspond, I'll make some notes here. Normally we say, well, that corresponds to e to the 2 plus 3i t. But what do? Well, we say that's really e to the 2t, then e to the 3it. And now that's when we pull out de Moivre's formula and say, oh, well, really, e to the 3it, that's e to the 2t. Then we have cosine 3t plus I sine 3t. So, distributing that through, we get e to the 2t cosine 3t, so that's the real part of that, plus I e to the 2t sine of 3t. Okay, so we took our eigenvector, split it up into real and imaginary. We took our eigenvalue, that corresponds to really this exponential, and we said, okay, that corresponds to this function, split that up into real and imaginary. And now the sort of the punchline of this, the thing that we're going to say that gives us our answer is we look at this and say, group the parts which are no I at all, so in other words, the real parts, and group the parts which have an I. So you can imagine that you do a foiling, right? Multiply first outer, inner, last. And they'll split into two camps. And each camp is a solution. And that's how we get our general form. So we can now write down our solution. So the way we're going to do it, so we're going to say x equals c. And now we're going to do our real parts. Okay, so let's we'll have a color here. So one real part would be there. So we're going to have our minus 1, 1, e to the 2t cosine 3t. So that would be our first terms. And then we're going to have the last terms. And there's an I squared. So that means there's going to be a minus. So minus 1, 0. So I squared makes the minus. And e to the 2t sine of 3t. Okay, so there we go. That's one of our two solutions. And then we're going to add to that d. And now we're going to do a very similar thing, but instead, let me see, I have to find a good color here. We're going to do the imaginary parts. So the imaginary parts would be, for example, the last pieces. All right, so we'd have minus 1, 1, e to the 2t sine of 3t, and then our inner parts, right? The outer parts, the inner parts. And so plus 1, 0, e to the 2t cosine 3t. And that's our general form, right? Because we're not after a particular solution. We're not after anything that solves an initial value. We're just saying, what do solutions look like? And the answer is, they look like that. And there we go. So, recapping. If we encounter something where there's complex roots, okay, find the roots. And that corresponds to, of course, a particular function, which we can break into real imaginary parts. Find an eigenvector. Again, we can break that eigenvector into real and imaginary parts. So we have our eigenvector split up, our function split up. We multiply out, and we group by keeping it real, making it imaginary. And those give us our two solutions. Put them together, and we get our answer. All right. Good. Woohoo! Nice. Nice. And wow, what a fun problem. What a fun problem. And we're halfway done. That means we still have half as much fun left to do. Cool. Good. Lucky us. Lucky us. Okay. All right. On to the next one. So, given the eigenvalues of this matrix A, and A is given to us, 1, 2, 1, 2, 2, minus 1, minus 6, 5, 6, are 3, 3, 3, and the only eigenvector is 1, 0, 2, right? The general solution for the differential equation, x prime equals ax. And you're probably thinking, oh, we got to go start looking for those other eigenvectors. Where are they? No. There are no other eigenvectors. This is a case where we came up short. We're missing some eigenvectors here. In particular, we're missing 2. So we have to work our way up. This is our bootstrap. Start from the bottom and find some vectors that help us get what we need. All right, so how do we do that? Well, let's begin. We'll call this vector, for reference, we'll call it v. And what do? Well, we look at this matrix A minus lambda I. So everything is going to be based off of that matrix. Now notice it's different than lambda I minus A. And I apologize for the confusion. If you want, you can always go with A minus lambda I, and then you never have to say, wait, which one do I need? A minus lambda I works in everything that we do for this class. Okay, so, but we definitely need A minus lambda I here. Now when we talk about minus lambda I, what we really mean is we're just going to subtract the value of lambda off the diagonal. And so we're going to subtract 3 off our diagonal entry. So we're going to get minus 2, 2, 1, 2, minus 1, minus 1, minus 6, 5, 3. Okay, And now we're going to work our way, we're going to sort of be bootstrapping our way up. And so we start at the beginning. Well, it's a very good place to start. And we already have v. So what we're looking for is we're saying, okay, we're looking for some vector w that would go to v. So it's like, oh, hey, what's something that goes to v? Now, if we do this right, we should have multiple options. If we do it wrong, we won't. So that's going to be a test. It's like, hey, do we have flexibility? And then once we have flexibility, we're going to say, let's pick a nice choice, make things easy on ourselves. We love ourselves. We love ourselves so much, we're not going to make it hard. All right. Well, that's the basic idea. So we're going to make augmented matrices and work with them a little bit here. So minus 2, 2, 1, 2, minus 1, minus 1, minus 6, 5, 3. So I'm copying the matrix down. And I will say, one of the biggest challenges in problems like this is copying errors. Because even if you copy just a minus sign wrong, and I've done that before, it breaks it. And so be careful. And I say that, now I'm paranoid, like, oh, did I copy it right? I'll do my best. But I just want you to know, oftentimes people get so caught up and like, okay, it's not working. I must have the wrong idea. It's like, no, you probably have the right idea. You just missed a minus sign somewhere. So don't panic. Relax. We're in a test. That's our happy place. Our happy place where we get to have fun. And then just look for that minus sign. Okay, so we're writing down v. And now we start saying, all right, let's clean it up. So I'll try to knock out some entries here. And I like to work in the first column. You can work in any column you like. In some sense, some of the later columns are easier to knock entries out because you see more ones. But the first column's not bad, so we'll do one times the first row, add it to the second row. And we'll do negative 3 times the first row, and add it to the third row. And if we do that, what will we see? Well, what we'll see that we haven't changed the first row. Not yet. Then when we add down, we're going to get 0, 1, 0, 1. Oh, hey, that's good. And then we 6, minus 6, 0. And then here, minus 6, 5, minus 1, minus 3 and 3, 0. And minus 3 and 2, minus 1. And now we're like, hey, wait a second. These two bottom equations are saying the same thing, right? Because if you think about what we're after our vector w1, w2, w3. Okay, so that's what we're after. So we're after w1, w2, w3. And what does this say? Well, the entries are telling us that w2 equals 1, minus w2 equals minus 1. In either case, w2 better be 1. All right, great. So now we have our great w2 equals 1. So 1. Well, we're not done. That's just one entry. There's two other entries that are up here. Now let's just look at given that we know w2 equals 1, let's come up here. And what do we have? We have minus 2 times w1, 2 times w2, which is plus 2, and then here, w3 has to equal 1. Or we could say minus 2w1 plus w3 equals minus 1, because we can subtract 1. Now, let's come up with a nice, easy solution. And there's lots and lots of solutions. When I say nice and easy, I like to make things very simple, zeros and ones, if I can. And I see, oh, if we make W1 0, we can make W3 minus 1, and that would satisfy this equation. Is that the only option? No, you could do things like, well, let's make W1 2 and W3 3. But I like to keep things simple. So here's a case where there's lots of possible answers, but try to keep things nice and clean. And remember, the reason we say there's lots of possible answers is you could modify it by anything that involves v. And all right, so if we set W1 to be 0, then we can choose W3 to be minus 1, and we're happy. Okay, so there are other options. In fact, we'll make a little note here on the side, just for people who aren't watching the video. Oh, those scalawags. Oh, I can't believe they wouldn't want to watch this. Who doesn't want to watch someone doing math for an hour and a half? So, well, since people played at, double speed, it's only 45 minutes. So many other options possible. But the point is, try to keep things simple. Simple is always a good option. Okay, so now that's great. So we've sort of like, okay, we found our second vector that we need. But we're not done. We have to do this another time. Okay, so our next iteration is going to be very similar. We're going to look for a minus lambda I, working our way through the alphabet in some really unusual fashion. I'll go with the letter U equals W, right? So the way we do it is we say, okay, we have our vector V. What goes to V? We found a vector W. Say, okay, great. We have our vector W. What goes to W? Right? That's how we do it. What goes to that vector we just found, and repeat it as needed. Now, the nice thing about the process is it's actually going to run the same way. And we said, oh, we only needed to really do one step in what we did here. So that's great. We can just repeat those same operations. Be careful here. It's not 1, 0, 2. It's 0, 1, minus 1. Make sure you put in the right pieces here. Okay, so again, I'm just going to copy what we did here, because these operations were to change the left-hand side. And so that works really, since it worked really well here, it'll work really well again on the left-hand side. So 1 minus 3. And what do we have? Well, we have at this point, we're actually going to have very similar things. So minus 2, 2, 1, 0. And then we're going to get our 0, 1, 0, 1. And we're going to get our 0, minus 1, 0, and minus 1. Right? Yeah. That's what we'll get. Right? Because you just copy down. Okay. Now, we're like, whoa, deja vu. We can actually copy a lot of the same things that we had upstairs, right? Say, hey, look at what this equation is telling us. It's telling us that these things have to, they're really saying the same thing, right? Because if we have our U1, U2, U3, it says, look, U2 has to equal 1. That says U2 equals 1, or minus U2 equals minus 1. Okay, and then the first equation says, well, minus 2U1, 2U2, but U2 is 1, so plus 2, and then plus U3 has to equal 0. Okay, so we could say minus 2U1 plus U3 is equal to minus 2. And now we just have to say, is there some nice, easy choice of U1 and U3 that satisfies it? And we have options. There's lots of options. We'll always have lots of options. If you don't have lots of options, mistakes were made. But the good news is we have options here. And again, in the spirit of, I like having lots of things where we have our ones and zeros. Well, we should, of course, note, we already said this has to be a 1. And I say, oh, minus 2u1 minus 2, we can make this a 1 and make that a 0. And if we do that, that'll work. That'll give us what we need. And beautiful. All right. Well, fantastic. Fantastic. And now you're like, okay, well, what does all of this mean? Well, this all means I probably need to grab another piece of paper because we still have to write down the answer. Okay, so let's recap what we have on this new piece of paper. So we had we could write it this way, a minus lambda I times 1, 0, 2 equals 0, 0, 0. This is where we started. That's our eigenvector. That's what it means to be an eigenvector. And then we said, okay, now we worked our way up. A minus lambda I times 0, 1 minus 1. Well, that equals 1, 0, 2. And then we said, okay, cool. A minus lambda I times 1, 1, 0. That's equal to 0, 1 minus 1. All right, so that's the work that we did. This was given to us, and because it's an eigenvector, and for our eigenvalue of 3. And then we said, okay, and oh yeah, we should make a note here. Lambda equals 3. And then we built our way up. So now we're ready to write down our answer. All right, so what is our answer? And you might say, wait, what was the question? So recall the question, general solution for x prime equals ax. Okay, so here's how it goes. So what we start is we say, okay, x equals, and we start with just our eigenvector. All right, and so in that case, we're going to have our c, then we're going to have e to the 3t, because lambda equals 3, times our eigenvector 1, 0, 2. Okay, so that's level 1. Now level 2. So level 2 is we're going to bump, and we're going to use both our eigenvector and our next vector up. So we're going to have plus d, again, e to the 3t. And here we take our eigenvector and we're going to multiply that by t. And then add this vector, plus 0, minus 1, 1. Okay, good. And now we go to our next entry. So we're going to use all 3. So plus capital E for our constant, and then e to the 3t, and then we have, we start starting at the eigenvector 1/2 t squared, 1, 0, 2. Then go to our next vector, t, 0, minus 1, 1. And then finally, the last part, 1, 1, 0. And that's it. That's the answer. That's the general form. Now, I will say it is possible that you might have something that looks slightly different. And the reason I say you might have something that looks slightly different is this vector, you can add anything where there's a 1, 0, 2 to it. So you might have had, 1, minus 1, 3. Perfectly valid. In other words, this can be perturbed by anything that looks like your eigenvector. And similar, this can be perturbed by anything that looks like your eigenvector. But the moral is, there we go. That's the answer. So this, again, the process isn't so bad. There's a few things you have to understand. You work your way up. How do you get from one vector to the next? And so that process is one part. And then the other thing that is just remembering, how does it all fit together at the end? How do you get your pieces in? But once you understand those two things, it's not so so terrible. It really becomes mechanical. All right, what a fun problem. That took like a page and a half. That's how you know it's a quality problem. Wonderful, top-notch, fantastic problem. All right, well, that leaves us with 2 problems. Probably time to help us do some Laplace transform. Yep. Right, because we've been holding on to our table. Okay, all right. Use the method of Laplace transforms to solve x double prime minus 2x prime minus 8x equals 0. And we're told that x of 0 equals 6 and x prime of 0 equals 18. And you're probably thinking, well, I don't need to have Laplace transforms to solve this, right? No, you don't, but we got to follow the instructions. If you don't follow the instructions, you won't get the credit. And we want the points, right? It's like we want to channel our inner Pokemon. Got to get them all. And so that's what we want. So we're going to follow the instructions. Okay, so how does it work by using the method of Laplace transforms? Well, we start saying, all right, we're going to take the Laplace transform of our differential equation, turn it into an algebra equation, solve the algebra equation, and then go back to where we started, which is going to give us our answer. All right, so we'll have Laplace transform of x double prime. And remember, Laplace transform is linear, so I can break it up in a nice way. Anything where I have subtraction or addition, that breaks up. And of course, I can pull out constants. So I have Laplace transform of x double prime minus 2 Laplace transform of x prime minus 8 Laplace transform of x equals 0. All right. And now we'll pull out our table here. And we say, okay, what do we do with things, for example, like x double prime and x prime? Well, it's on our table. It tells us. So for x double prime, s squared x of s. And subtract s of x 0, subtract x prime 0. Okay, so then what will we have? Let's work through this carefully here. We have that the first piece, that'll become our s squared x of s. All right, subtract s times x 0. X 0 is 6. So subtract 6s. And then subtract x prime is 0. So subtract 18. All right, so that's our first piece. And now we go to our second piece. Okay, so this part. So we're going to subtract 2. And what do we do here? Well, it's s x of s. All right, s x of s. And then subtract x 0, minus 6. All right, great. And finishing up, well, we have the part here. Well, that we don't even have to think about. That's just the transform. And all of this equals 0. We didn't write down the Laplace transform of 0, but it is the case that the Laplace transform of 0 is 0. Okay, great. We will come back to our table if we need it again. And we probably will when we go back, right? The table helps us sort of go back and forth, right? We start with the differential equation. The table helps us write the algebra equation. Now we're in algebra mode. And then once we're done with the algebra mode, then we go back to our table to get back to functions. All right, so, okay, putting on our algebra hats here, we can group the things which have x of s together. So that would be s squared minus 2 times s minus 8 times x of s. And then we have a minus 6s. And then we have minus 18 plus 12. Don't forget the minus 2 goes through. So minus 18 plus 12 would be minus 6 again. Oh, okay. Well, that's no problem. Minus 6 equals 0. Okay. Well, move the parts without x of s over. So we are s squared minus 2s minus 8 times x of s equals 6s plus 6. All right. Now what? Well, to get x of s by itself. Because really what we're doing is the algebra involved, and really there's two things. There's the isolate your x of s, and then write the part that x of s is into nice pieces. And that's usually a partial fractions going on in that step. So we can say, hey, x of s is 6 times s plus 6 over s squared minus 2s minus 8. Now, we can do, hopefully, fingers crossed, the denominator will factor. So what are we looking for? We're looking for two numbers that multiply together to give negative 8, but add to give negative 2. Not a lot of options, but negative 4 and 2 work. So that says, oh, s minus 4, s plus 2. So, okay, great. Now we have our factorization. Okay, so time for us to put on our partial fractions hat. So we're going to grab a different color as we do our partial fractions. So we have our 6th s plus 6 over s minus 4, s plus 2. Well, we break it up according to the downstairs. So downstairs says, hey, you have to have a particular form. So we have two terms downstairs. So we're going to have something over s minus 4, something over s plus 2. And we're going to put constants. So this is one of the most important steps in partial fractions, is knowing, what does my answer look like? Because once you know what your answer looks like, you're like, oh, okay, all right, that's what it is, right? Okay, and then you go from there. Clear your denominators. Okay, so to do that, we're going to multiply both sides by the quantity s minus 4, s plus 2. Whatever this denominator is, clear it out. And that'll lead us to the following equation. 6 times s plus 6 is going to equal to a times s plus 2 plus b times s minus 4. And now is our, let's make good choices. We should always make good choices in life. And so what's a good choice? Things that can make zeros. If we can't make good choices, we'll do other techniques. But I always like to say, try to make good choices first. And so, for example, suppose we choose s equals 4, because that would knock out the second piece. 24 plus 6 makes 30. And then here, 4 plus 2 makes 6. So we get a times 6. So that says a has to be 5. Wow, we're halfway there. Another good choice? Well, negative 2. That would knock that term out. And if we do that, we get negative 12 plus 6 would be negative 6. 0a. And over here, minus 2 minus 4 minus b times 6. So we get b is negative 1. All right. Oh, what, positive 1? Ah, I forgot there. Both sides are negative. Yes, positive 1. Good, good, done. All right, so what does that tell us? Well, now we jump back and say, hey, x of s, we can use our algebra result to say this really looks like a, which is 5, over s minus 4, and b, which is 1, over s plus 2. Okay, and now where to go from here? Well, we've now pulled it apart. And the reason we were doing that is because we wanted to say, hey, we've got our table, and we want to make our pieces look like things on our table. This thing does not look like stuff on our table. But s minus 4, that looks a lot like that. It shows up on our table. So we're like, aha, this is great. And in fact, we can push this over to the side a little bit here. And we see, if I see 1 over s minus something, that corresponds to our exponential function. So we're now ready to go to our answer. So we're ready to go inverse Laplace, go back. backwards. So x of t, which is what we're looking for, would be equal to the 5. Well, we don't need to worry about the 5 because this should just have 1 upstairs, so that just comes out as a constant. And then s minus a, 1 over s minus a would become e to the 4t. So 5e to the 4t plus, and then 1 over s plus 2. Well, think of that as s minus minus 2. So that would be e to the minus 2t. And we're done. That's it. Aha! Woohoo! Yeah! We did it! We did it! We solved our differential equation. Good. Good. Well, that's what we want to do, right? We want to solve all of the problems. So this is a pretty straightforward Laplace transform problem. But a lot of Laplace transform problems have this feel to it, right? We take the Laplace transform of both sides, use our table to clean it up, run through algebra to rewrite it so that we actually have stuff that looks like our table entries, and then use our table to go back. And we get our answers. All right, good. Well, that's number 5. One more problem, and we'll be done. Number 6. Okay, recall that ERF, and you're probably thinking, what? Recall? I don't ever recall seeing ERF before. So ERF is a function. It shows up a lot, for example, in the statistics. And I think it may have shown up on some of your homework problems. So what is it? ERF of t, 2 over root pi, integral 0 to t, e to the minus tau squared, d tau. All right. Thinking, wow. So that's ERF. Is there like a Papa ERF and a Brainy ERF and maybe an ERF-et? No, just ERF. Just ERF. Okay. Well, what are we going to do? We're going to find the Laplace transform of ERF of root t. Okay. Wow. Okay. Now, it says, in addition to what is given in the table of Laplace transforms, we have that. The following might be helpful. I suspect that when they say the following might be helpful, it probably is going to be helpful. It says, hey, if you have a Laplace transform of t to the b, that's gamma of b plus 1 over s to the power b plus 1. Now you might say, wait, that's not on our table? Well, the table has t to n, where n is a whole number. Suspicious. Even more suspicious, they tell us gamma of a half is square root of pi. And the other thing they say is, hey, if you're taking the Laplace transform of the integral from 0 to t, f of tau d tau, that's the Laplace transform of f of t divided by s. And say, okay, well, this involves an integral. So, hey, there's some pretty good ideas going on here. All right. Now, how do we put all this together and get what we need? All right. Well, we have to be careful here, because you'll notice, you might say, well, wait, how do we go from this to there? Because you're like, oh, I see an integral 0 to t, and I see an integral 0 to t. You're like, aha, that's perfect, right? But if we look a little closer, we want to actually do ERF of root t. So we're looking at the following function. So ERF of root t would be 2 over root pi, integral 0 to root t, e to the minus tau squared d tau. So we don't exactly match that. So now we have to sort of step back for a second and say, what's going on here? And this is a time when it comes down to saying, do you understand what the concept is saying? In particular here, the important thing is when you look at this part versus this f of t. How do those two relate to one another? Well, what you have is that this is an antiderivative, right? If you integrate a function, you get an antiderivative. and it's an antiderivative, which happens to be equal to 0 when you plug in t equals 0. Now, the good thing is, if you plug t equals 0 into this, you get integral 0 to 0, which is 0. So that's good. And so what we should think of is we say, okay, if we want the Laplace transform of this, we can think of ERF as being this part right here. It's an antiderivative of something. It's not an antiderivative of e to the minus tau squared because that's root t, but it's an antiderivative of something. Whatever that something is, that's what goes there. So what's the derivative of ERF? Root t. All right. So what do we need to take the derivative of this? I'll tell you, it's something from calculus, and it's a fun part. Yes, it's the fundamental theorem. Exactly. We're going to do the fundamental theorem plus chain rule. Jazz hands. All right, so we're going to put those two things together. Okay, so the 2 over root pi will stay in front. That's a constant. And now the fundamental theorem of calculus says, hey, if I want to take a derivative of the integral, it's the inside function, but I plug in my bounds, right? So the 0 just goes away. It's plug in the bounds, which are the varying bounds. So this would be e to the minus square root of t squared. All right. Now, I said chain rule. What else do we need to do? We have to multiply by the derivative of square root of t. So derivative of square root of t, well, half comes down, t to the minus 1/2. All right, so that's the derivative of the ERF function. So fundamental theorem of calculus with the chain rule. Let's clean that up. Well, the 2's cancel. That's good. So we have 1 over square root of pi. And then we have e to the minus t, and downstairs t to the 1/2. Or you can leave it as t to the minus 1/2. Maybe I should leave it as t to the minus 1/2. That feels more calculus-like. And the reason I say more calculus-like, calculus is often built off of rules where it's t to a power. All right, so what does all of this mean for us as regards to this problem? Well, what it means is the following. We said, hey, if I have a function which is 0 at 0, then the Laplace transform of that function is the Laplace transform of the derivative divided by s. Well, I have a function which is 0 at 0, so the Laplace transform of the ERF function at square root of t, according to the rule, is going to be equal to this 1 over s, Laplace transform of this thing. 1 over, no, that's an s. It looks like a 2. Sorry about that. What? No, it looks like a 5. That's an s. 1 over square root of pi, e to the minus t, t to the minus 1/2. Okay. Well, we can certainly bring out the square root of pi. And now we look at this and say, okay, what do we have? Well, e to the minus t, t to the minus 1/2. And we start thinking about our rules. Now, we know how to handle t to a power because that was given to us. But what about the fact that we're multiplied by e to the minus t? So now we come back to our chart. And we say, okay, what happens if you multiply a function by an exponential function? It's actually the second item on our chart. So if I multiply any function by an exponential function, the result is shift the Laplace transform at the end. So if I'm multiplying by e to the t, that would be a equals 1, I'd shift s minus 1. If I'm multiplying e to the minus t, I'd shift s minus minus 1 means s plus 1. So the e to the minus t means we shift the answer. And now we're like, okay, because if you covered up the e to the minus t, it's exactly what we have here. So according to this, we would have 1 over square root of pi times s, and then we would have gamma of b, so b is minus a half minus 1/2 plus 1, got excited, and that's minus half plus 1, and then downstairs we would have s plus 1, because remember, we're shifting because of that e to the minus t to the power minus 1/2 plus 1. Okay, so 1 over square root of pi times s, and gamma of 1/2, and then downstairs s plus 1 to the 1/2. But what is gamma of a half? It's square root of pi. So this part right here is square root of pi. And then we say, hey, square root of pi cancel out. And so we get a nice answer, which actually doesn't involve any pi at all. So there's s, and then s plus 1 to the 1/2, square root s plus 1. And there's our answer. Last problem, final answer to our practice. Wow. That's kind of a really amazing function, right? It's so clean. You look at this function like, it looks terrible to work with. And then you come over here and like, ooh, well, that looks nice. What a nice function for us to play with. And it is indeed a beautiful, beautiful function. All right, well, I hope you've enjoyed this practice, as you do enjoy all practices, I'm sure. And keep working. And the reason we do practice is so that we can feel confident and prepared when we go into the test. I want you to do well. I don't want you to be nervous. You'll be fine. Keep going. And I'll see you again.